Welcome back. This time we've got a refraction problem. Okay, so this one's going to feature a little bit of Snell's law and a little bit of geometry. In this one, we have light entering a triangular piece of glass shown over here on the right. So this is the light ray that's entering. And notice since it's entering at basically 0 degrees incidence, that means it's just going to go straight through. Okay, so there's no refraction at this surface here, at the first surface. But it enters a triangular piece of glass with index of refraction 1.48. It strikes the slanted face, so the second face here, at the critical angle for that surface. And what we want to do then is we want to find out what this angle alpha is. And then if we want light to be transmitted out of the glass at this point, in other words, if we want light to come out of here instead of just being totally internal, undergoing total internal reflection, should we increase or decrease this angle alpha? Okay, so let's start with the first part. Okay, we want to know, well, basically this light strikes this surface here at the critical angle, and we want to know what this angle alpha is. Okay, now first of all, just a reminder that angles in general, the critical angle and angles that you use in Snell's law, those are all measured from the normal, or in other words, a line perpendicular to the surface. So this is the surface we're talking about here. And so the normal is going to go kind of like this, so that this dashed line I've drawn should be perpendicular to this one. Okay? And the critical, if this, the angle of incidence as this light strikes the slanted face here is going to be this angle here. Okay? Now, we're told in the problem that it strikes at the critical angle. So this is going to be the critical angle here. So first of all, let's figure out what that is. Okay? The critical angle we know is given by theta c equals the arc sine of n2 over n1. Okay? And remember, n1 is the surface, it's basically the first material, and n2 is the second material. Okay? And so this is arc sine of, so n2 is out here. Okay, and so I'm assuming this is air. Okay, so that's going to be 1. I probably should have stated that in the problem. And then N1 is this material here. Remember, we're talking about when the light hits this surface here. And so that's why this is N1 and this is N2 out here. Okay, and N1 we know is 1.48. And so this tells us then that the critical angle is about 42.5 degrees. And so that's what that angle there is. Okay? Now, what we actually want to find is this angle alpha here. But if this is 42.5 degrees, then this angle has got to be 90 minus that. Okay? And notice that this angle here is in fact equal to the angle alpha. So alpha is in fact going to be 90 degrees minus 42.5 degrees, which is 47.5 degrees. Okay? So that's what the angle alpha is. All right, so that's the answer to the first part of our question. Okay, second part of the question. Now, of course, this is the critical angle, and what that means is that at this angle, we get total internal reflection at this boundary, which means that none of the light gets out. Okay? Now, if we want some of the light to get out here, then the question we're asking is, should we increase alpha or should we decrease alpha? Okay? Well, here's the way to think of this. Basically 42.5 degrees is the critical angle, okay? If we want light to get out, then what that means is we want theta 1 to be less than 42.5 degrees. Okay, in other words, light will escape if the angle of incidence is less than the critical angle. If the angle of incidence is at the critical angle or greater, that's when we get total internal reflection. Okay, so the question is, basically we're going to take alpha here and we're going to make it either larger or smaller, meaning we're basically going to take this side and either swing it out that way or swing it down that way. The question is, which of these is going to make this angle smaller? Because that's what I want. Okay, now basically what that's going to come, well, what I have to do in order to make that happen is I actually have to increase alpha. Okay, let me see if I can show you why that is. I'll try and convince you of that. Okay, if remember that this angle here is the same as alpha. Okay, because of the fact that this line and this line are parallel. And so if I increase alpha, I'm also increasing this angle here. And since this angle and this angle have to add up to 90 degrees, that means if I'm increasing this angle, I'm decreasing this angle. Okay? And that will put me below the critical angle, and that will cause light to escape the glass at this point. Okay? Here's another way you can think of it. If I want to make this angle smaller, which means that I want this dashed line to swing up like that. And to get this dashed line to swing up like that, I have to take this back face here and have it swing out like that. Okay? So basically I have to increase alpha in order for light to be transmitted out of the glass at that point. All right, we're done.